All right, let's take a look at our first discontinuity. We're going to call this removable discontinuity. And the name itself explains it in its continuity. I can't spell, so I'm not even going to attempt. Removable discontinuity, or we also know this as a hole in the graph. So there's a hole in the graph. All right, this is not going to meet the very first requirement for continuity where we said f of c must exist when c is an element of the real number. So it's not going to meet the first requirement. And the reason why is because there's a couple things we know about fractions. So I have a rational function here, which is a fraction. We know we can never have 0 in the denominator. So right now, if I look, I have x plus 4 and 2x minus 1. If anytime those equal 0, I've got a problem, and that's really where our discontinuities are going to come from. The removable part is we want to factor all the time, and this one's in factored form, but we want to factor everything, we want to factor rational functions all the time, and then we're going to look to see if we can reduce the fraction or if we can remove something from the fraction, hence removable discontinuity. So discontinuity is going to come when our denominators are going to be equal to 0 as far as in pre-calc. All right, so if I look here, I have x plus 4 over 5x minus 2 and x plus 4 over 2x minus 1. Well, I can actually cancel out this x plus 4 and this x plus 4 and reduce my function to f of x equals 5x minus 2 over 2x minus 1. That's easy enough. That's just simplifying a fraction. But we have to remember that my x plus 4 cannot equal 0. And if I solve this, I know x cannot equal negative 4. Well, that means if I put negative 4 into this function, the original function, it's not going to work. I'm going to get 0 over 0. And that's an indeterminate form that you'll study later on in calculus, but we can't do that, 0 over 0. So what we're going to need to do to get rid of this 0 over 0 is we're going to use a table, and I'm going to use some notation here. So we're going to kind of explain what's actually going on at the graph right around negative 4. So a couple things on the notation. We're going to start using limit notation. So I'm going to say the limit as x approaches negative 4. Now, if you notice, I put a minus right here. That minus means it's coming from the left. An easier way to think about it is I need a number really close to, but a little smaller than negative 4. So to the left of negative 4 of my function f of x. And I'm going to do a table x, y. Then I'm going to set it up, and it's coming from the left. My other option is to come from the right. So I'm going to say the limit as x approaches negative 4 from the right of my function f of x. And I'm going to do the same thing, x, y, and a little xy table. All right, so I need to pick a number to the left of negative 4. Be careful, it's on the negative side. So this is, I'm going to pick negative 4.1, negative 4.01, and negative 4.001. I want to get as close as I can. I want to get pretty close to negative 4, but I can't do exactly negative 4 because I would have 0 over 0, which we can't do. So then all I'm going to do is take this, plug it into the original equation. When I do that, I'm going to get 2.989. That's where I take this negative 4.1 and I plug it into this equation right now. Next, I get 2.999 when I put 4.01. And next, I might as well just say it's 3.0. It's still rounded. It's not a perfect 3. But I can see a trend. As it's getting really close to negative 4, it's trending like it's really close to 3. So we can say that limit's going to exist is 3. So as I'm approaching from the left, negative 4 from the left, I'm approaching the y value of 3. This is your y value. This is your x value. So let's do the same thing for the right. So here I'm going to do negative 3.9, negative 3.99, negative 3.9. Now when I do that, I get 3.01, 3.001, and we might 0 because I'm rounding. It's really a whole bunch of zeros after that when I plug these numbers back into this. So we can actually say that this is actually 3 as it's approaching, as we're approaching on the graph from the right towards negative. So that's it. It's approaching 3 and 3. Oh, you know what? I forgot. We could have done this a lot easier than using. All I had to do was plug -4 in here, because there's a rule in calculus. So I could have just done f of -4 in my reduced function, which would have given me 5 times -4 minus 2 over 2 times -4 minus 1, which gives me -20 minus 2 over -8 minus 1 gives me -22. What the heck did I do? Did I mess up my equation? Yes. This number right here, 7. Oh, what happens when you the problem? So now, when you put these into that equation, you get these numbers. This becomes a 7. This becomes 7. I get -27 over -9, which equals 3. So my whole, which is a point, is going to be the x value of -4 and my y value of 3. Careful you write down your problem correctly, because I have my problem here. And I started with the problem, but I changed it, and I forgot to change it here. And that's why I forgot to write a 7, so I got a nice pretty number. So make sure whenever you're working problems, you are writing down the question correctly right off the bat, or everything else could be wrong. Hi, I'm Mr. Buzzard, and these videos are supplemental instruction for my students. If you found the video enjoyable, make sure you click the like button and click subscribe, as well as the bell for notifications to receive future videos on high school mathematics.